Well, here we begin in our discussion about calculating the surface area. That's what we're doing. The area of a surface is created by revolving a parametric curve about either the x-axis or the y-axis. For now, let's assume that we're rotating about the x-axis. Okay, so let's make sure that we understand that. Rotate about the x-axis. Let me write that here. Okay. Now, the little sketch I've shown here, and I'm not too interested right now in really worrying about what this surface looks like. Let's see if I can give some idea, though, if we could get an idea of this surface. If we rotate that, then I'm going to act like I'm imitating or having exactly the same surface here. It's not going to be exactly the same the way I'm doing this. Okay, play like that's the same. When I rotate it about the x-axis, then I'm going to have a mirror image here, aren't I? Now when I do this rotation, so I'm going to have something, if you look here and there, okay, that's more or less what we're going to have. Now, the way we did this before is we took a piece of this and thought about that is, we took a piece of the curve itself and thought about rotating that piece right here. So I'm talking about this piece right here, okay, right there. Think about rotating that around the whole surface, and it gives us a frustum. Remember that idea that we discussed a long time ago? And we ended up doing a lot of work to find out what that surface area of that one strip is. And what we found out is the surface area of that one strip. Let me call dA. dA is the surface area of the strip. Okay. Now, let me imitate over here, but I'm going to have to expand that. Let's suppose we're talking about this length right there. And what we've basically done is, like we did before, we're breaking this whole curve into little tiny lengths, and we're thinking about rotating each one of those little tiny lengths, and we'll find the surface area of what we get of that rotation. Now, that once again is a ds. Okay, that once again is a ds. And what we found out before is that, remember that this surface area ended up being 2 pi times y times ds. Now, we did a lot of work to do that. But it boiled, when we were doing this before, but it boiled down to, and I'm oversimplifying, but if we think of that strip and we cut it, then we have a strip laid out like this. Now, this isn't exactly what we did before, but this is what it resulted in. And now, one of the things that we need to know about the length of that strip is its width. And this width is that ds value. See, I laid it out, but it's the width of that strip all the way around. Now, the length of that strip is actually the circumference of that strip, or that circle that we make when we go all the way around. And so this being a circumference is 2 pi times r. But the radius in this case is actually the distance from the x-axis to the curve. Okay, distance from the x-axis to the curve. That's the y value, or r. Excuse me, r. So what we have is that we know r is actually a y value. So this is 2 pi times y. That's what we have there. So that's where all of this business came from, that all we're doing is multiplying the circumference. That's the circumference, and this is the width, if you will. So the circumference becomes the length, this width becomes the width, and that's the area of that strip. Okay. But we just calculated, that ds can be, remember we're doing this in parametric equations, and so we want something in terms of t's, our parameter t, whatever our parameter is. And we just decided on the previous pages that ds can be replaced with the square root of the derivative of x with respect to t squared plus the derivative of y with respect to t squared dt. So that is the area of one micro-size, infinitely small strip of infinitely small width. So the surface area that we're looking for, okay, the surface area in total, and we'll call it capital S here, would be the integral of all of the dAs. That is, we're adding up all of the surface areas of all of those strips. They're infinitely small, and there's an infinite number of them, and that's what integration does for us. And we're going to start that. Well, let's look at our curve. The first t value is t subscript a, and the last t value is t subscript b. Now, of course, we have a replacement for dA. So the surface area is equal to the integral of, now what is it we have? A 2 pi. Let's go ahead and factor the 2 pi out. So it's the integral, 2 pi times the integral from t subscript a to t subscript b of y times the square root of derivative of x with respect to t squared plus the derivative of y with respect to t squared dt. Now, if we assume, because we have parametric equations, if we assume we can write x as a function of t, f of t, and y as a function of t, g of t, then we could rewrite this a little differently, couldn't we? Okay? If we revolve around the x-axis, then what we get is the surface area. The surface area is equal to 2 pi times the integral from our first t value to our last t value, and y is g of t, times the square root of, now x is f of t, so the derivative of x with respect to t is nothing more than f prime of t. Of course, that's squared. Plus the derivative of y with respect to t, well, y is g of t, so that's nothing more than g prime of t squared dt. That's what happens that's the way it looks if we revolve about the x-axis. Now, we can go through the same arguments if we revolve about the y-axis instead. Then we'll get our surface area is equal to 2 pi times the integral from our first t value to our last t value, and instead of a y, we would have an x, and our x would be f of t. And then it would be the square root of the same thing. It would be square root of f prime of t squared, sum of f prime of t squared and g prime of t squared with respect to t. Remember, this is just x, and remember, oops, this is just y, my bad. I was thinking down here, and this is just x in this case. So it could be replaced with a y and an x likewise. This is if we revolve about the y-axis. So let's see how we can use this in a actual problem. Okay, in this first example, we're to find the area of the surface formed by revolving the curve, the parametric curve, defined as x equal cosine t, y equal 1 plus sine t for t's between 0 and 2 pi. We revolve that curve about the x-axis. Now, setting this up may not be that difficult, but I'm going to take a little detour here so that we can kind of see what it is we're actually doing. Now, normally we would probably just set this up and go about our business and calculate the surface area. But what I would, this is a curve that we would be somewhat familiar with in what we did previously. Well, maybe we haven't done it yet, actually. I'm sorry, I'm thinking out loud here. If we were to eliminate the parameter here, if we were to eliminate the parameter, the kind of thing we've seen about eliminating the parameter in the past is that we've used the identity cosine squared t plus sine squared t is equal to 1. I know normally we say sine squared t plus cosine squared t is equal to 1, but obviously either way. Now, in this particular case, cosine of t is x, so we could replace this with x squared. I'm eliminating the parameter, remember. Now, sine t I don't have, except that I see above y is equal to 1 plus sine t, so sine t is actually y minus 1. And so here we have instead of a sine of t, we have a y minus 1, and that's squared, and that's equal to 1. Now, as soon as we do that, we recognize what we have here is a circle, isn't it? This is a circle. And it's a circle that looks like this. The center has an x value. The center has an x value of 0 and a y value of 1, and we have a radius of 1. So we would have the center right here, and the radius is 1, and so we would have a circle that looks something like this. Okay? So that's what we're dealing with. Now, we're going to rotate that about the x-axis. Now, you bear with me. In fact, I think what I'll do is draw the rotation, and you're just going to have to bear with me because this is a three-dimensional object I'm trying to create. So let me draw that, and then I'll come back. Well, I'm not particularly happy with that, but that's the best I can do right now. So if we think about that circle being rotated about the x-axis, then it looks kind of like if you will, a sausage that we've connected the two ends of the sausage, but we've done it real tightly. See, it's just think of a tube, and think of rotating that tube, kind of sticking one end inside the other, so that there's really no space in the middle. It's kind of like taking, another way to think of it is kind of like taking a donut and poking holes in the middle of that donut, but real narrow holes, so that it doesn't really have a hole, it just goes down to a point. I hope that makes a little bit of sense of what we're actually doing. Okay. Well, maybe you can see that. I hope so. Anyway, let's set up our problem. We don't really need that diagram, but it's kind of nice to know that that's what it looks like. So to calculate the surface area, okay, S is going to be an integral of 2 pi times y. I mean, remember, we're rotating about the x-axis, so it's an integral from a t value, and in this case, well, let me just write it this way. The beginning t value to the ending t value of 2 pi, earlier we factored out the 2 pi, didn't we, times y, times the square root of, and the y is because we're rotating, because our radius, remember 2 pi times y is actually our circumference, not of the circle, but of our rotation strip. Okay, 2 pi times y times the square root of the derivative of x with respect to t in this case, squared, that's our parameter, plus the derivative of y with respect to t squared, and that integral is with respect to t. So we just start filling in the pieces. Our surface area then is equal to the integral from, well, our first t value is 0 and our second t value is 2 pi. And that actually takes all of those to create the entire circle. I've been a little lax there. We need to recognize that we get the entire circle when x is 0, t is 0, and then when t is 2 pi, it creates that entire circle. Anyway, times 2 pi. Our y value in this case is 1 plus sine of t. Times a square root. Now the derivative of x with respect to t, the derivative of that's the derivative of cosine, isn't it? Which is negative sine t. And that derivative is squared. Plus the square of the derivative of y. Well, the y is 1 plus sine t, and so the derivative of y is just, what, cosine t? And of course that derivative is squared. And we're integrating with respect to t. Well, what we have under here is really sine squared plus cosine squared t, isn't it? See, that's just a 1. So this is the integral from 0 to 2 pi. Let's go ahead and factor out the 2 pi that we have inside the integrand of 1 plus sine of t times 1. Well, we don't need to write that. Okay, dt. Well, now this is pretty straightforward. Here's our 2 pi outside the integral. The integral of 1 plus sine of t with respect to t is t plus the integral of sine t is negative cosine t, isn't it? Whoops, negative cosine t. And we're evaluating that from 0 to 2 pi. That is, what we're doing is we're taking 2 pi times t minus the cosine of t. That's what I should have written first. And evaluating from 0 to 2 pi. Well, when we do that, you can finish this out. There's no big deal here. We'll get 4 pi squared. And we could approximate that if we wanted to. It wouldn't be a big deal, but right now I'm satisfied with 4 pi squared. That's the surface area of this surface that we get by rotating that circle about the x-axis. Let's do one more of these problems, and this is actually to find the surface area of a sphere. So, and we have a formula for that, but now we'll see how formulas like this are actually derived to begin with. Well, here a problem is stated that we're to find the surface area of a sphere of radius capital R. And without using the formula, obviously, we're going to develop the formula. Now, if I left off the last part, we may be a little bit lost of what we're going to do. What we're actually going to do is use the surface area formula when we're revolving a curve about the x-axis. Okay, that's what we're doing here. So we have to set this up so we get a sphere by rotating some curve, some parametric curve about the x-axis. Now, a sphere of radius r is a sphere of radius r no matter where we locate it. So I'm actually drawing this sphere so that the center of the sphere is at the origin, if you will, but of course the sphere is three-dimensional. So I'm thinking, of course, this is the y-axis, and this is the x-axis. And so when we get finished rotating, we're going to have a three-dimensional object. So, we've got that extra dimension here when we rotate about the x-axis. Now, what is it that we're rotating? See, that's the first thing. What is it we're rotating? Well, here's what I'm going to suggest that we do. Let's rotate the upper half of a circle. That is, let's do this. Let's imagine this semicircle. Okay? Let's imagine this semicircle. Okay? Now, if we take that semicircle and we rotate it about the x-axis, then this is the object we're going to get, as long as this semicircle has a radius, if you will, of r. As long as it has a radius of r, then that's the object we're going to get. We're going to get that sphere. So now we have to decide how in the world we're going to come up with an equation for that semicircle that's a parametric equation. So here's what I would suggest that we do. Imagine any location on this semicircle, then the distance to the origin to that location is capital R. And of course, now that creates a right triangle. We could create a right triangle so that the horizontal leg is x, and the vertical leg, of course, is y. And we'll assume this angle right here is t, and measured in radians, so that makes sense. That angle is t. We could say theta, but I'm going to call it t. Well, now, if we look at that, then what we recognize from long ago is that the sine, let's just think here, that we'll say the cosine of t. The cosine of t would be adjacent over hypotenuse, and so that would be x over r, capital R. So we could define x as capital R times cosine of t. And in a similar way, the sine of t would be opposite over hypotenuse, and so that would be y over capital R. And we could solve for y, and we'd get y is equal to capital R times sine of t. Now, what t values do we need? Well, to create every position on that semicircle, we need to start t's at 0, but they only need to go to pi, don't we? So our parametric curve that we're going to, rotate is defined in this way. X is equal to capital R times cosine of t. Y is equal to capital R times sine of t. And t, our parameter, is between 0 and pi, not 2 pi, pi. Now be careful, we wouldn't want to rotate the entire circle, would we? That would be another thought. But if we rotate, let me make a point here, rotating the whole circle would create two spheres. Because the upper half of that circle would, if we rotate it all the way around, and that's what we're talking about, would create a sphere. The lower half would follow up and create another sphere. So we'd have one sphere on top of another, and we would be getting two spheres. They'd just be together. Rotating the whole circle would create two spheres. So we wouldn't want to rotate the whole circle. That's the reason we're just doing the upper half of that semicircle. Okay. And also notice that normally we would say theta, but we can name our parameter anything we want to. And in this case, I've named the parameter t, just so it fits a little better. So we set up our integral for the surface area that we get here. And remember, we'll factor out the 2 pi in advance, and we're going to integrate from our first t value, which is 0, to our last t value, which is pi. And what are we integrating? Since we're rotating about the x-axis, we're integrating y times the square root of derivative of x with respect to t squared plus the derivative of y with respect to t squared dt. So we have a 2 pi times the integral from 0 to pi, and y is capital R times sine of t. Now, under the radical, the derivative of x with respect to t, since x is r cosine t, then we get what? A negative r sine t. So we have a negative r sine of t, and that's squared. That's the first derivative, the derivative of x squared, plus the derivative of y squared. Well, the derivative of y, since y is r sine t, is r cosine t, and that derivative is squared. Now, what we'll notice here is inside the radical, okay, let's pay attention to that right now. Whoops. And the upper limit of integration is pi, r sine of t. Okay, inside the radical, what we really have is an r squared sine squared t plus an r squared cosine squared t dt. And so we see that, and maybe I'm taking too many steps here, we see that we can actually factor out an r squared from that, don't we? So we have a 2 pi times the integral from 0 to pi of r sine t, and underneath the radical, we actually have an r squared times sine squared t plus cosine squared t. And of course, sine squared t plus cosine squared t is nothing more than 1. So under the radical, we just have the square root of r squared. Now, remember, capital R is a radius, so it's a positive number, and so the square root of r squared is simply r. We do know it's simply r. So we have 2 pi times the integral from 0 to pi of r times the sine of t times the r we get from that radical dt. So we actually have an r squared there, don't we? Well, let's go ahead and factor that r squared out. So now all we have is 2 pi times r squared times the integral of 0 from 0 to pi of simply sine of t dt. And now we're ready to go to work. Okay. The integral, of course, the integral of sine of t is negative cosine of t. And we're evaluating that from 0 to pi. Well, negative cosine of pi then subtract negative cosine of 0. And of course, cosine of pi is negative 1. So we have the negative of negative 1 subtract the cosine of 0. Okay, that's what we have here in the beginning, isn't it? Right here. Minus the negative cosine of 0. So cosine of 0, of course, is 1. So this is the negative of negative 1. Well, that's positive 1 plus 1, isn't it? So what we end up with, and I've kind of run out of room here, what we run into is we have 2 pi r squared times a 1 plus a 1, which becomes, of course, 4 pi r squared. So the surface area of a sphere of radius capital R is 4 pi times capital R squared. And now you could go look up in your geometry formulas and you'd see that's exactly what we get. Okay. I think that's an interesting problem. Well, this finishes our discussion. I think I said this earlier at another time, but this finishes our entire discussion about parametric equations. First, what they are, we did, and then we talked about the calculus of parametric equations when we found derivatives, and when we found tangent line slopes, equations of tangent lines. What else did we do? We found second derivatives, didn't we? We found second derivatives. We found out when points where we have horizontal and vertical tangent lines. And then we finally went into arc lengths of parametric curves and now surface areas generated by revolution of parametric curves. So that's our entire discussion. Good luck on your homework, and I'll see you in the next lecture.